Mein Name ist Hellmar, ich bin bei Confluent, ich bin Solutions Engineer bei Confluent und ich erzähle heute ein bisschen was über Apache Kafka und Kubernetes, was eine spannende Kombination ist, die im Moment ziemlich viele Leute interessiert. Also, Kubernetes und Apache Kafka als Distributed Event Streaming Plattform. Ist das okay, wenn ich auf Deutsch weitermache oder gibt es Leute, die kein Deutsch verstehen? I can do it in English as well, which is fine. Yeah, I can also do it in English. Okay, so this is about Kafka and Kubernetes. Kafka is a distributed event streaming platform. Kubernetes is a cloud orchestration platform. And, well, how these two play together, let's start with this one. This is actually a book that I have been using quite a lot when I taught myself about Kubernetes. This is Kubernetes Up and Running. And the main guy behind this is this guy, Kelsey Hightower. And he has firsthand experienced a lot of things where he said, yeah, well, okay, so first of all, you have Kubernetes and you deploy your stuff on it, but we still have some issues with stateful workloads. So basically anything that requires processes, pods, we'll come to pods later, to be identifiable, anything that keeps state anywhere. And he says, yeah, well, okay, yeah, I still prefer not to run them on Kubernetes. Now, of course, because we know what Kafka is not only an event queue, but also an event store. So it is by its very definition. It is stateful. And so the same guy said Kubernetes can only meet stateful workloads halfway, and I lack the expertise. So the Kubernetes guru says, I lack the expertise to manage a production configuration of Kafka, and so on, and so on. Well, yeah, so some work to be done, but actually we noticed that, yes, this work has to be done. So don't despair, says Franz Kafka. Kafka, because the Kafka software itself was developed by some alpha nerds, people that like to read, people that wrote software that can write a lot of data, so it was also kind of natural to use something as use a name of somebody who also wrote a lot. Don't despair, because there will something new will be coming that is from Kafka's diaries, and I even looked it up in German, although in my slides it's now in English. Okay, so now to recap. Kafka. What is Kafka? What does it? The problem that we try to solve with Kafka is pretty much this. This is what we like to call an organically grown data integration architecture, right? Yeah, that's what we call it. So you've got all kinds of applications, you've got a data warehouse somewhere, and somebody decided to add Hadoop to it, and something happens here in batch mode, there's something here that might be elastic, and somehow, while there are these somehow near real-time databases and the cache here, and it is very, very difficult to keep an overview, it's very difficult to maintain, and yeah, people notice it's difficult to scale. That's the next problem. You add a new data store, you add more data, and that is what's happening nowadays. People say, we want to have all those transaction data. We do want to have not only transaction data, but every single interaction with our customers that may eventually result in a transaction. So all of a sudden, you blow up your data volume by an order of magnitude or two, and it still needs to fit in all, yeah? Okay, and then you have some pipelines in between there, some messaging systems that are difficult to scale, others where nobody really knows how to work them up to new data sources and data sinks. Sometimes, I don't know, I mean, maybe some of you have worked in enterprise scenarios and you know it has all been built up to enterprise quality standards, and then, so it goes from here to here, enterprise standard, and from here to there, also enterprise standard, and then there's this little piece of glueware that some guy wrote in some scripting language. Sounds familiar, I see a smile over there. Anybody seen that like that? And this one guy is the only one who knows this software, and he's all about to retire, and yeah, so these things happen, yeah? So wouldn't it be nice to have something like this? So you have a central hub where you can put in all your data, you can get out the same data in real time, and no matter who is going to send data, like produce data, no matter who consumes these data, it's all safe. You have got certain guarantees in here about persistence, about ordering of your data, about not losing anything, about exactly one's processing, and well, that's what we want. And then here, enter Apache Kafka. Okay, so this is our event streaming platform architecture. So we've got these brokers. These are the ones that receive all the events and they hold them for anybody who wants to consume them, because it's a publish and subscribe system. The system is highly scalable. Anything that is sent into a so-called topic. So imagine a topic like a channel, or if you come from the database world, it's like a table, although it's real time. And this is set up into, or it's split into partitions, so that if you write, and even if you really hammer this cluster, you are always communicating with several servers, with several of these brokers, and they can handle the load. Typically per machine about 50, 60 megabytes per second, that's like a standard. Behind it, you've got another service, and now why is this not coming? So we've got, behind it we have got a Zookeeper, so it's a small cluster, which is concerned about the bookkeeping. So what is Zookeeper? Who knows what Zookeeper is? A lot of people know it, not everybody. So Zookeeper is basically, I like to say, it's a distributed, very, very highly consistent key value database that knows what is, in our case, knows what is running where, it knows which brokers exist, and if any one of these fails, then the Zookeeper service can detect this and it can rebalance the data. The Zookeeper also can detect if any of the servers here is down. It needs to have a majority vote on what is going on. And this is why you have always 3 of those at least. You might also have 5, or in rare cases 7. Okay, on top of this, we have, and no, it is again not coming. So we have got applications that can communicate directly with Kafka. So this is very, very standard. It's still Apache Kafka setup. We have, and this is something that we created at Confluent, we have a schema registry which makes sure that the data, that basically Kafka itself doesn't care about what you send to it. So Kafka would accept any data, because for Kafka, base Kafka, it's just binary data. Now, more often than not, you've got data that are structured in some way, and you want to make sure that any application can only send and can only receive those data that it is prepared to receive. That's what the schema registry is for. And then there are other parts of the platform. There is Kafka Streams, which gives you the possibility inside the Kafka ecosystem to do processing with your data in real time. So you can join several topics. You can join data together. Say you can join customer data and transaction data. You can join, if you have a connected car, location data and speed data. You can join data from different production machines. You can filter your data, you can aggregate your data, you can do time windows over your data, all that you can do in Kafka Streams. And well, that is a Java library. And then on top of that, we have got KSQL. And if I have time left at the end, I will come to KSQL a little bit more, which is an application development language on top of Kafka Streams. That is really cool. And then we've got Kafka Connect, which gives you standard modules that connect the Kafka cluster to any kind of data source or sink that you may imagine. In addition, and also this is something that you can get from Confluent, we've got a REST proxy. So for any application where you cannot really write code, you don't have a standard connector, you can always use a REST interface. I've got 2 REST proxies here in order to have high availability. you can do that. You would have to put your own load balancer in front. It has a little star because you don't get that one from us. Your operations people have to set that up. So that's just to complete the picture. And now, that was very, very quick high-level overview of Kafka. Now, very, very quick high-level overview of Kubernetes. Where is this whole Kubernetes hype coming from? Well, yeah, so back in the day, when I was young, we had monoliths, yeah? So you had an application, somebody wrote that application, you would just dump that application onto a server and it would do something, and it has some external connections, and that's it. If you want to change something, you have to change the entire application, monolith. It's somehow out of fashion. So we started talking about microservices. Yeah? So instead of having one monolith that you have to take completely and deploy it as one, change it as one, have complex processes, you've got several components that are loosely coupled. And you think you have solved your dependency problem. Well, it's probably going to bite you back, but that's another story. And now this is microservices. It's still classical deployment. So you have a service which, at the end of the day, is an application. The application runs on an operating system. It needs to support certain features of the operating system. It needs certain libraries. It needs versions of those libraries to be present. And in order to solve these problems, we included Docker. Yeah? So Docker gives you containers. Hey, containers were all the rage like 2-3 years ago. And we started with Docker containers. Yeah, so you can actually bundle all your dependencies. You can bundle your libraries with your application into a container and just dump that container on your server. So you are independent from the underlying operating system. You're independent from whatever may be installed on that server. Cool thing. And then, okay, so now what do you do with your containers? You still have to put these containers somewhere. You need to be able to tell what container runs where and how they talk to each other. And that is where Kubernetes came in. So there we are. And it is nicely summarized in this tweet by one of the gurus again. Yeah, so first we said we must adopt microservices to solve the problems with monoliths. Then we must adopt Docker to solve the problems with microservices. And now we must adopt Kubernetes to solve all problems with Docker and with the containers. What is it that Kubernetes does? Kubernetes does orchestration. Orchestration is how I organize, how I deploy, how I distribute several things. So it comprises several functions: computing resources, networking resources, storage resources, and to discover what is where, service discovery. So these are the key points, the most important points of orchestration. And what Kubernetes does is it schedules and allocates resources. It takes care of networking between pods. Now, what is a pod? I might have a later picture about it, but let me just tell it now. So a pod is basically a set of containers that are always supposed to be deployed together because they need to be together. So like a pod are two tightly or several tightly coupled components that form a microservice. Kubernetes takes care of storage, and Kubernetes takes care of service discovery. How does it do that? Now, you have a cluster. This cluster has some nodes. You build this node typically before the fact. So you could run this on bare metal. You can run this in any cloud. Some clouds have predefined services to help you get up and running with Kubernetes. You've got a Kubernetes master, and you talk to this Kubernetes master through an API, either through command line or through a user interface. And with that, you tell Kubernetes what you want to deploy on your cluster. The basic unit of deployment, and I just said that, is a pod. A pod is not something you should eat. A pod is a collection of containers that have a common namespace, a common network, and common volumes, so data storage. And these pods are what you deploy on Kubernetes. And you say, okay, so this is a pod, say, Kafka Broker. And I want to have 3 of those. And what you tell Kubernetes is, in a declarative syntax, so you do not say, throw this on server 1, 2, and 3. But you tell Kubernetes, I want 3 brokers running. And I don't care how you do that, because how this is done is the task of Kubernetes. Kubernetes knows what kind of resources are available on the nodes, how much memory, how much CPU, and so on. And if it has the necessary resources on certain nodes, it will deploy software there. It will deploy the pods there. So this is about the software itself. Then you have got storage. Storage has 2 things. It has persistent volumes and persistent volume claims. Both are called resources, but they're actually different things, because a persistent volume is a piece of storage. So basically you could, very, very much simplified, you could say it's a disk here. So it gives you so much storage, and it makes sure that this storage is not erased. It's provided in a dynamic or static way, and it can be used by any pod. So, and then there is a persistent volume claim. This is where a user says, okay, I want to have storage. And then this claim can be fulfilled by a persistent volume. Now this is important, because Kubernetes basics, so when you start reading with that Kubernetes up and running book, then it gives you stateless pods, which is cool. Oh yeah, I just throw these pods, I say I want to have 3 of them, and I don't care about the rest, because if they fall down, nobody cares. You bring up a new one. But a Kafka broker is different, because the Kafka broker has storage, and it needs to. This storage has data that need to be remembered. You can't afford to lose them. So that is where you add the storage. So therefore, enter stateful workloads. So stateful, it means so these pods somehow have some data that still need to survive. So if a pod dies, then, well, you bring up a new one. Kubernetes does that for you. But you also need to make sure that that new one takes over the data from the old one. So that is where the stateful comes in. So what you need is a service that does something that is not in the basic Kubernetes deployment. For a basic Kubernetes deployment, if I deploy one pod 3 times, then Kubernetes cannot tell the difference. They are like, twins or triples in that case. So they don't have an identity. You need a service that actually knows, okay, this one, number 0, 1, and 2, they are different. They are individuals all of a sudden. And this service knows about this. So it gives them an identity. And, therefore, it can deploy stateful workloads. Now, in order to deploy these kinds of workloads, we are using an open source tool called Helm. What is Helm? Well, Helm is also something that has been developed by the developers of Kubernetes. It works with YAML files, and you can imagine it as a kind of package manager for Kubernetes. So Helm knows, okay, in order to have a cluster of XYZ, I want to have, like, remember the architecture that I drew before with all those Kafka brokers and Zookeepers and the Kafka Connect there and the schema registry there. So basically, I would tell it in a YAML file, okay, I want to have 3 brokers, I want to have 3 zookeepers, and so on and so on and so on. There is an instance which is called the Helm Tiller, to stay in the metaphor, yeah, right, on the cluster, and this one is regularly monitoring the Helm file. So basically, I deploy this YAML file into Helm, and when I change it, then this guy here checks, oh, something has changed, and based on that, I do something over here. So if I say, oh, I want to go from 3 to 5 brokers, then this guy says, oh, there's a change. So what do you do here? And then Kubernetes knows, oh, I need 5 instead of 3, so I bring up 2 more. Or the other way around, if I scale down, then I bring down 2. So this is how Helm works. I start with those YAML files, the Helm client, which is on my controller machine, reads these files, deploys them into the cluster, and the Helm Tiller sees there's a change and communicates with Kubernetes in order to adapt the deployment. One of my colleagues has done a very good movie about that, which is available on YouTube. So this is Viktor Gamov. He is the senior guy. Actually, I got most of this talk from him, and he is on YouTube, and there you can see exactly how these things work. So basically, what Helm does is you package multiple resources into a so-called chart, and the chart is like a map of what your cluster is supposed to look like. So, in order to deploy a Kafka cluster, but actually the other thing is you need to do it in the right order, because before you can even bring up a Kafka broker, you first need to have this Zookeeper running. The Zookeeper is very, very central to everything in Kafka. So, okay, you need a Zookeeper. The Zookeeper wants storage, so you need to give it a storage claim. You need to have a stateful set for, in this case, 3 nodes Zookeeper. You need to program anti-affinity, which you need for high availability, because, well, if you lose a server, you don't want 2 or 3 Zookeeper servers to be down, because then you are basically done. So you make anti-affinity to make sure they all go to different machines. You have this headless service that gives the 3 Zookeeper servers an identity, and you also make sure that you get your JMX metrics from all this. So now you've got your Zookeeper. Next step is you set up your Kafka brokers, and so they use the same service as the Zookeeper. They have their own storage claim. They have a stateful set for n nodes. They've got node and port services, so you can expose the brokers to external traffic, and they also have this JMX configuration. So, well, the problem here is, and this is the real tricky point. So this is all, okay, yeah, you have got your Helm, you deploy them, and then everybody is happy. But it's not quite like that, because once you have to bring something back up, or you scale up or you scale down, then you actually need to know a little bit more because of all this statefulness and because of these brokers having their own identities. You need a so-called operator component. The operator is something that knows the data more exactly. So it knows once you have to reconnect the broker because another broker went down, then the operator knows to which storage this broker has to connect. The operator knows how to do backup and restore. The operator knows how to rebalance. Like if you bring in more brokers, you also want to have existing data on those brokers. And it does regular health checks and makes sure that your configuration matches the desired configuration. And this is actually a component that also runs inside the Kubernetes cluster. Then there's another component which is called a controller. Each Kubernetes resource basically has a controller behind it. So you've got a replication controller, a namespace controller, and so on and so on. And this is all done using the Kubernetes API. So if you have resources that go beyond the standard Kubernetes things, Then you have a custom controller. And once you have defined that, you can access the resources of that controller with standard Kubernetes commands. So, to summarize it, you can, with the operator, this is Confluent Kubernetes operator, you can deploy and manage your streaming platform on Kubernetes. You can do automated provisioning, you can do platform operations, you get your metrics, you get your resiliency, you get your monitoring through JMX integration. The operator knows about the special things that each Confluent component needs to know, things like security, like network services, fault tolerance, scaling, how to scale. And with that, you get your automated cluster deployment. So it looks as simple as this. So here you've got, for example, you say, okay, I've got my Kafka brokers. Each of those has 0.2 CPUs, 1 gigabyte of memory. Well, it's a bit small now, but so this is how it has been set up. And just by installing this Helm chart into my cluster, I tell Kubernetes, okay, I want to have these 3 Kafka clusters, and because the operator is running, it knows exactly what to do about Kafka, what to do about when a broker fails, and that each broker is its own individual. So if, say, I want to size up my cluster, I want to scale it, then I can just go and I tell it, oh, I want to have 5 Kafka brokers now instead of 3. So I just edit this file. Actually, what I do is I do a Helm upgrade command. So I deploy that new YAML file into my cluster, and it will do automatically. It will do everything for you. It will do a rolling upgrade because I've also changed the version here. It will stop those brokers that need to be replaced. It will make sure that, so it waits for leader election to complete. So it means that whenever it stops an individual broker, it will bring the cluster back into full operational state. Then it will start the new broker in the new version, make sure that everything is good again, rinse and repeat, and it will do all that for you. All you do is enter this one command. And this is the really cool thing about it. So, to summarize it, I need to go here. You can automate your cluster provisioning, you can scale up and down, you can monitor your own SLAs, and with that you can operate at scale, and you get support from Confluent. So, this is the main thing that I wanted to talk about today. I have a few more slides about KSQL, if anybody is interested. Otherwise, I would just open up for questions now. KSQL. Okay. KSQL, and that is something that I personally like very much. Okay, so how to start with KSQL? If you want to write a stream processing application, event streaming. Now, there are tools out there, probably, who has worked with Spark? Some people, okay. Who has worked with Flink? Nobody? Okay, so Spark comes from the batch world. Data scientists use it. Flink is owned by Alibaba now. And then we've got Kafka Streams. Kafka Streams is a Java or Scala API on top of Kafka, where you can take data out of existing Kafka topics and you push them back into new topics. And in between, you do all kinds of nice stuff with it. So you've got your typical map and filter and list and window and so on operations that you can use to write, well, to query your data in real time, to do things to your data in real time. Now, the thing that is annoying for some people is that you need to be able to write Java or Scala, and while a typical Java developer will say, oh yeah, well, that's nice, I'll just do that quickly, then somebody who doesn't use Java every day said, oh, wait a moment. I have to, before I can do anything here, I need to install Eclipse or another development environment, and then I've got a million dependencies, and then I need to install some Maven stuff, and then it will download half of the internet before I can do anything. Ah, no, I don't like it. And then you lost them already. Actually, they only had a little business problem. And back in the day when we did batch, actually somebody came up with SQL, because with SQL, you don't really need to care about, what library am I going to use here? How do I chain together my commands in order to arrive at a certain result? You basically have a declarative language that says what I want to have as the result and not how to arrive there. So in order to make things easier for those people who are not hardcore developers, there is KSQL. And this is basically the graph that shows how, you make it easier, you reach more people, you get people really to leverage the power of event streaming, real-time event stream processing with a declarative language. And I can only encourage you to try it. There's a user interface, there's KSQL, you can use it from the command line, and there's a REST API here as well. And this is really nice, there's a headless thing. So what does it mean, headless? It means, actually, you can deploy an entire application by just issuing a SQL command. So what you do is, and this is probably too small here to see it, yeah. So what you do in KSQL, and actually it's probably at another occasion I might return here and I'll do this entire talk about KSQL, where I have concrete examples and I'll show how this all works and how to do it interactively. So you write a query. So instead of having a what you know from the database world, where you say create table X as selects star from Y, and then you do all your magic. So the same works here, only you say create stream X as select star from Y, and then once you start this query, as long as your Kafka cluster is running, it will still continue reading data from the input source or sources, and it will continue delivering results. Now, you do that interactively, you have an interactive query. You do that by deploying it into a KSQL cluster, and you have an application. You have an application that takes some input data and it continually produces output data. So, just in the same way that you can have a Java application that reads data continually and writes data continually back to Kafka, you can do a KSQL application. It does not run on Kafka brokers. It runs outside the Kafka broker cluster. It runs on a cluster of its own, but that's the next slide. And this one will continually read data and write processed data back. And just like a Java application, a Java stream application, your KSQL also scales. Yeah? You can just build up and set servers next to each other, and you can have its own cluster that scales. It is resilient. If you lose a machine, then another machine will take over that machine's data. You never lose any data. And once it comes back, then it will take over its load again. So you never lose anything. The state behind it is in a distributed database, and it makes sure that no state is lost. So if you want to get an idea about when to use what, well, yeah, so one is KSQL, SQL statements. It has a UI. It has a command line interface. It can, this is one of the limitations, it can only read certain formats because it requires schema structure that currently it can use Avro, JSON, or CSV. It comes with a REST API. It comes with an included runtime that is the KSQL server. So unless you have some very specific requirements like querying the state database, the internal state directly, you can do basically everything with KSQL. Kafka Streams, so that's a Java API, gives you full flexibility, but in the end, what you do is, you do here something, you say, okay, I have a stream, and then I do stream dot map so-and-so function, dot filter, dot window, and each of the, and then group by, and each of those actually translates directly into a SQL clause. Filter translates into a where clause. A group by in Java translates into a group by in SQL, and so on. And this is how this is actually much easier and much more non-hardcore developer friendly, much more also analysis friendly in the end. So, to summarize this, you start with the basic Kafka APIs. Yeah? So you've got something where you can read and write data. So you've got very basic calls here. So you've got subscribe. You subscribe to a topic. That's what a consumer does. He subscribes and then polls, so reads data out of the topic. The producer will send data, and everything else you do by yourself. Okay, next stage is you use Kafka Stream, where you have these more complex operations. Yeah? Filter, map, join, aggregate, transform. But it's still all in Java. You write your own Java applications. It builds on top of the basic APIs, and it shields this complexity away. On top of this, you've got KSQL. KSQL builds on top of Kafka Streams. It hides away some of the complexity, and then you've got very, very familiar looking SQL statements. Create table, select, join, group by, and so on. So, depending on your needs, what more up, more high level, is easier to use. If you need the full flexibility, you go down the stack. And this is the high-level overview of how, in this picture, the new ETL, real-time ETL, can look like. So you've got whatever data comes in. This here is a social media stream, yeah? You use Kafka Connect, a standard connector, to extract data from that and send them into the Kafka cluster. Within the Kafka cluster, you can use KSQL, a streaming application that is written as a single SQL statement to transform your data. It builds on Kafka Streams, but you don't need to bother about that. This is handled by Kafka for you. And then you can use Kafka Connect to write these data back to whatever data sink you want to use. It could be your data warehouse, your business intelligence tool, your Kibana dashboard, you name it. To learn more about this, we've got resources. So these are mainly the Kubernetes-related resources. There's a slew of interesting things on the Confluent website. There are Confluent blogs. There are free tutorials. So please feel free to peruse anything of these free resources. There's also free ebooks about Kafka that can be downloaded on our webpage. So with that, I say thanks. And I guess you're all very hungry, but maybe we can still open up for a couple of questions.
Regarding this type Kubernetes, could you expose this some details? Is it built on top of Kubernetes API? How does it function?
It uses the Kubernetes API. I know there is a standard operator library, but actually we started development on that before that operator library came out, so we are using our own libraries for that. So it's actually a proprietary binary that has been developed by Confluent. It communicates with Kubernetes and uses the Kubernetes APIs. Mm-hmm.
So the operator is only available if you have the Confluent platform, and in a productive environment you utilize the Confluent subscription database?
I think if you use it in production, you would need a subscription. However, we have this new setup where if you use for development purposes only on one machine, then it's free forever, so you can try it out. Yeah?
Are there any disadvantages regarding performance, especially when you run it under high load? And if you have the Kafka and Kubernetes, is there any disadvantage in having it on the plain infrastructure?
So the question was, is there any performance disadvantage? And well, as far as I know, the overhead by Kubernetes itself is very small. So you might, depending on what actual infrastructure you have below, you may have some performance trade-offs. So say if your persistent volumes actually run on shared storage, then you need to be aware very much of how to tune this correctly. But so not per se.
Okay.
Yeah?
Is it possible to integrate this operator somehow to cloud implementations of Kubernetes, like Kubernetes?
You mean like?
AWS, Azure.
Well, so the question was, can I integrate this with standard cloud implementations of Kubernetes? Actually, I got it running on EKS, so AWS, and so I trust it would also run on any other. Yeah. Okay. Thank you. And I think the pizza is also there. You're probably all hungry, and you're probably now happy that I'm finally done. So, thanks for having me. Enjoy the evening.